So Prof. Normiza also successfully supervised multiple PhD and master students and contributing to the next generation of engineers. In terms of patents and innovations, Prof. Normiza also ada a good innovator. There are several patents in grounding system, including methods and devices to enhance their safety and efficiency lah. So sangat sangat pakar lah Prof. Normiza ni. So itu saja saya rasa daripada saya untuk introduction kepada speaker kita hari ini. So we are indeed privileged lah to have Prof. Normiza with us today. So please join me in welcoming her as she present her lecture bertajuk Measurement of High Voltage and Currents. Okay, please welcome Prof. Normiza. Saya akan end saya punya presentation dulu and then Prof boleh continue with your presentation, okay?
Alright, okay. Thank you so much, Dr. Hazia.
Okay, no problem.
Okay, Assalamualaikum and very good morning. So today, okay, let me project my presentation slide first. Okay, so can you see my presentation slides? Yes? Yes or no? Okay, that's fine. All right. Okay. Okay. Before I begin, I have to apologize because there is I tried to use my pen this morning. However, it's not really working because this computer has just been formatted. And then another matter is I didn't put the this presentation in my handphone. So if you have any concern, like you can't hear me or you have any question, you can always stop me at any time during my lecture. And then, but you have to voice it out because I only see my screen. I do not have linked it to my my handphone, so I'm not able to see, you know, responses without any sound. All right. Okay, so today we are going to do this topic, measurement of high voltage and high current. Actually, if you refer to this one, high current, to this high current, I can say that in most testing we hardly have this application, except for certain test loops. Such as resistive loop, like linear resistor or surge arrestor. For that reason, then we normally use high current measurement. But of course, for the high voltage, as you know, that for other equipment such as transformer, switchgear, insulator, those mainly, or cable, those application is high voltage. So you can also see that in this topic, we explain more about the high voltage rather than the high current. And in fact, if you look at in many high voltage labs, in fact, in Malaysia itself, that most of the generating equipment they have is high voltage, and similarly for the measurement, hardly into the high current. All right. So you will see that the component of these slides have mainly the high voltage component rather than high current. In fact, if you see the textbook as well, they have mostly in high voltage and small parts of high current. Okay, so the outline, high voltage and high current. I have the, first I will begin with the introduction, and next I will, second part B, measurement of high voltage, where actually there are many, but I will focus on the three main components because of limited given time to extend it to other types of measuring device. So we will look into the sphere gaps, uniform field gap, and voltage dividers. So these are also the typical measuring device in many high voltage lab. There are of course other types as well, such as generating voltmeter, electrostatic voltmeter. They are still in use and highly accurate as well, uh, with a good precision, but because these are common and because of limited time, so I will just cover for these three measuring device. And as for the measurement of high current, as I mentioned before, that some high voltage labs, which is understandable that they do not have this high current measurement because the equipment that testing are not into the current evaluation, but rather on the performance of the equipment, which can simply be observed from the measurement of high voltage, which can be adequate. So, but anyway, we still have some introduction and just in case that in future you come across this high current measurement, then you are familiar with these three devices here: resistive shunt, Rogowski coil, and current transformer. And another part is partial discharge measurement. Actually, in at MMU, we normally categorize this under testing because, but anyway, we will include this also. Hopefully, we have time for this, and then we try to see the typical measurement setup for the partial discharge and why we need to have this partial discharge measurement. Because this partial discharge measurement is not only conducted in the lab, but also at field site. And also this partial discharge measurement, other than at site, other than the offline, it can also be monitored online nowadays with the digital substation, digital technologies. So we're able to actually observe it online as well. So we will just look into this because like for any equipment or most equipments, we want to see the health of the equipment online as well as offline. So we will cover this part as well, which is part D here. So the measurement of this one, I put the introduction, measurement of DC, AC, and impulse. I think that you may have covered the generating voltage already, where we have 3 generating voltage, DC, AC, and impulse are the basis for testing. So it means that, for example, you are working for the manufacturer and then producing the transformer. So this transformer will have to go certain tests before it can be sent or delivered to the customer. And of course, this test at the manufacturing level, normally they would have to come up with the manufacturing data sheet, where this data sheet should have all this information, and this information will be used by the potential user or buyer, and then will be according to their specification and requirement, and they would use it in their application. So for the manufacturing side, for example, then it has this requirement that also have to be fulfilled and have to be tested in the accredited lab, high voltage lab. So it has to go through this testing. So how do we know that this measurement that we or the testing that we do, provide the right results or accurate results and following the spec as required? So this very much rely on your measuring device. So if your measuring device is not accurate, it means what represented on your manufacturing data sheet may also not be accurate. So that's why it's important for this measurement, not only to understand, but also to ensure that it provides the correct reading and reliable reading. Okay, so that's why it is important to have correct and reliable voltage measurement techniques, so that the performance of the test load. Test load here refer to transformer, insulator, switch gear, all these capacitive equivalent circuit representation to be characterized accurately. Okay, so the measurement technique should prevent flashover because later we will see the typical arrangement of the test load and during the testing, and then we have to make sure that, okay, so if I just show here so that you have some picture. So for example, this is the testing in the lab, okay, in the lab, and then you also have this measuring device. So if you can see here, this is the capacitive divider. I can see that this can be capacitive divider. This could be the shorter one, could be the resistive divider. So this capacitive divider, when connected to this impulse generator, so you can see here, the one that I pointed here, impulse generator, and then it should not, this is when they are doing testing on the transformer, so it should not cause flashover. It means it should not be the source of flashover. If it is for the flashover, it should actually, likely come from the equipment, maybe some faulty or flaw in the equipment, but not from this capacitive divider. So it should not be the, in other words, part of the test load, because the test load here is your transformer. So that's why that's what it meant here, that the measurement technique should prevent flashover and heat dissipation, because heat dissipation is the one that you consider as the test load. It means that if you have some void or some failure in the transformer, then that can give harmonics, heat dissipation. That should come from the test load. It should not be from the measurement techniques. Okay, so in a summary, you can say that it should not be a load or test load of the system. So the oscillation or anything like that you observe in the results, in the test result, should be reflected purely or from the test load only, because the measuring device should not be part of it, because the purpose is just to measure. Okay, so some of the techniques used are listed below. So this is even though we cover only 3, but you can see there are a few more types. Like for DC voltage, there are a few types like resistive divider, generating voltmeter, as I mentioned before. While for the AC, potential divider can be used for all voltages or types of voltages. But for the AC, you can see here series impedance emitter, electrostatic voltmeter, sphere gaps, and impulse voltage are typically potential divider, peak voltmeter, and sphere gap. Okay. So you can see that some of this equipment, like potential divider, can be used all. So it means that if the high voltage lab, they buy one potential divider, so it can still be used for all kind of voltages. But certain equipment can only measure for certain type, such as the generating voltmeter. We don't use it for the impulse. This should just be for the DC voltages. Okay, so these are the testing. What is the purpose? Of course, we want to measure the voltage, basically voltage and current, when we do the testing on this equipment. These are just some of the equipment, such as transformer, circuit breaker is not here, but you can see lightning arrestor and bushing, as well as the insulator here. And if you can see, I'm sure that you have covered this in your testing, because like at MMU, we have measurement and testing. So the testing, we have learned about how to do the setup and so on. But for your case, you can see that this is the capacitive divider. This is the resonant transformer, maybe covered in your generating circuit or generating of high voltage. So this is resonant transformer. So this one is basically you can see in the testing, this part here is the insulator. The insulator, it has to be above the ground because it provides clearance. So this one you can also see when we go through the spark gap. Spark gap, we also have the clearance that has to be to provide space, safety space from the not only from the ground but also from the surrounding. This one here is the, I'm sure Dr. Hazia already covered it, but anyway, just to share with you, this is the DC, sorry, this is for the DC, this one, and then this one for the impulse generator, whereas this one is AC, resonant transformer. This one is not very clear to me. Okay, so let's look at for our measurement. Okay, a typical arrangement, this one covered normally in the testing. A typical arrangement, or in fact, when you do the testing in other subject as well, maybe you come across this already, which is the source. Okay, you can say that this is the source, and then this is the zinc oxide or the test load, and then this is the current measurement, normally shunt current or current shunt here. And then parallel to that is the voltage device or measuring device, which in this case is using the voltage divider. So this is the typical arrangement. I think that if you do other subject as well, such as circuit theory or back from your first year or power systems analysis, normally this is the arrangement where the voltage measuring device is in parallel with the test loop. Okay, but as we all know as well, this arrangement can suffer from inductive effect in the measuring loop. So when you reintroduce the loop here, and then the physical size of the transducer, then it will have inductive effect. So inductive effect, of course, it can cause some delay. Sorry, Dr. Hazia, I do not have my pen here for some reason, so I'll try to draw with my mouse here. So you have the delay, whereas the response of the impulse, it should be fast response, for example. So it means it's sharp here, and then it decay like that. But because of the presence of the inductance, then you have this delay here, right? So you of course we do not have this response, because when we have this response, it means that your equipment is not characterized according to the spec, because the spec say you have to produce the fast response, which is direct forward. This is coming fast response from the generating circuit, and then also apply here still fast response, but because your measuring device and because of the inductive component that you have inductance here, I mean equivalent circuit representation, so it will give the output as delay here. So whereas in the manufacturing data sheet, what you have to present is as this one here, which it should give 1.2 stroke 50. I think you have learned this one before, right? 150 microsecond for the impulse. So because of this inductive effect, then it gives different results. It means that your measuring device will give you not fast response as 1.2/50. So that's why it is important to first normally calibrate the measuring device before we proceed prior to the real test. But that one we will cover in general how to do this calibration test. I know that because I didn't see how your syllabus is, but I know that testing is normally included in the high voltage engineering subject. Anyway, here, so the voltage measurement, amplitude rise and decay times, very much influenced by the characteristic of the test load. So if your test load is nonlinear, then you may have more delay. It may not be a problem if your test load is linear load, because linear load you tend to have this similar characteristic. But if your test load is capacitive load, like capacitance, because we know that your equipment just now, such as insulator, cable, transformer, the circuit representation is the capacitive. So when combined with the inductance, so now you have the L and C in the circuit. So when you have L and C, what happened? What happened to this smooth, fast response time? So it will be like this. You may have oscillation here, and then before it goes like this. So of course, you do not want to have this initial oscillation on the voltage reading. Then because how you going to put it in your manufacturing data sheet? If the buyer see this, of course, they are not convinced with the equipment that you are measuring. Because so that's why the high voltage test engineer, they have to make sure that this is being calibrated, and at the same time the measuring device should be in other words adequately accurate, because they have some tolerance as well, like 10%, 30% and so on, and should be represent the real results that similar to what impinge on the test load. So this is the ideal process lah. I mean, if you want to assess this output, you have to have free, of course, losses, free from inductive effect. Inductive effect is of course, because you have the cable, you have connect all this large size, as it says here, large physical size of the equipment. Of course, it has the inductive effect. And then another challenges with the impulse test is that the inductive effect is more significant under high voltage or under fast transients, because we know that fast transient here, it refers to 1.2/50 microsecond. So 1.2/50, if you convert it into the frequency, it means that 1/1/2, or in other words, 1/1 microsecond, for example. So in terms of frequency, then it becomes, what is it, in megahertz, right? In megahertz, because the time is, so I put here in megahertz. So when it is in megahertz, the inductive effect, you know, the formula is X, what is it? 2 pi L, right? 2 pi F, L. So inductive effect here becomes higher because your frequency is high, because it is in the range of mega ohm. So for this reason, the inductive effect is, you know, one of the determinant factor in determining whether your measurement is correct or your measurement is giving the correct and reliable measurement. So this have to be reduced or minimized. So in order to reduce that, normally there are certain ways. One way is you able to know it from the calibration, and then of course to minimize the use of the loop in the circuit, or the physical size of the transducers. So other factors is the initial, so this is the one that I mentioned before. When you have the inductive effect, then you have this initial oscillation. So this is the condition when there is no inductive effect. Actually, this one is obtained by the P-SPICE simulation. So when we didn't put any inductive effect, you can see that the response is as the required, which is giving 1.2/50, whether it is for the linear load or non-linear load. But when you have the inductive effect, of course, in the P-SPICE, you have to put the component of the inductive effect in the test circuit, and then it shows that when you have the non-linear basically, or mostly, you see the oscillation. And then when you have the inductive effect, then the current will also be delayed. You have some current, slower current rise time here. Whereas when you have no inductive effect, it gives or the real reflection of the test load. But the circuit is influenced by the inductive effect, therefore is giving the different measurement results. So inductive effects of the test circuit with the so because of the inductive effect when combined with capacitive effect of the test load, because test load, as I mentioned, that it should be in general represented by the capacitive component, like cable, switchgear, insulator, it should be capacitance. So when combined with the capacitance, then it can give oscillation. And this one is also the same, inherent inductive, and another capacitive component other than from the test load is also from the voltage divider. So which we will see the component of the voltage divider, especially the the capacitive divider, like this, the high arm and low voltage arm. You have this capacitive at the high voltage arm as well as at the low voltage arm. So when combined again the L and C, so it gives you the oscillation here. So arrangement of the test load some distance away. This is also when you have some distance from the test load and the transducer, as what you've seen here. Then some distance away, especially if we run the test by the field measurement, then you may come across this mutual inductance, which give you this oscillation again. So not only the inductive effect give you oscillation, it also change the results. In other words, you can see here the nonlinear now becomes very much delay. The current response becomes having or exhibit slower current rise time compared to when you do not have non-inductive. Okay, so when we analyze this, of course, then we will be, we may think that it's due to the test loop, whereas it's actually due to the inductive component in your test arrangement. Okay, proposed method to reduce this. So how we overcome this, for example, there are certain ways, but this is like more for the research purposes, like coaxial arrangement, series divider, and D-dot probe. So this is, of course, this is not included in here. Just let me go back to this list again. This D-dot probe, coaxial arrangement or series measurement, you can see here is not, because as I mentioned, that those are mainly for the research. But if you go to many high voltage lab, normally these are the typical measuring device that they use. So these are like to reduce this more towards the research purposes only. But how we overcome this, if we are like, a practicing engineer or testing engineer at high voltage lab, so that one, normally we of course minimize the distance, and then we normally do the calibration test first, and then of course for the measuring device there are certain factors that they consider in their design, so that in other words they consider this inductive effect, and they minimize those inductive effect in the design of the measuring device. So that's why for the practicing the high voltage lab, and even for the manufacturing, they have this basically consider this measuring device that reduce or minimize the inductive effect. But anyway, I just even though as I mentioned before that those are basically the research purposes, but that these are the preventive action or something that you can consider in future, like how to reduce this inductive effect. But for the research, they have this method where you can see here that when they use the typical arrangement, then they have this spike, or in other words, small oscillation here on the voltage, whereas the voltage should be, a fast rise time without any spike. Because if you see this measurement, our impression is that our, when we see this when we do the measurement, of course we connect it to the oscilloscope, oscilloscope, and then when we observe this, then what is our impression? We may think that something with the component in the test loop, whereas we if you have the knowledge that it could be inductance, it could be other parameter, then you may want to do calibration test first. So that's why this knowledge is important, especially when you deal with the measuring device. So but actually this spot here is actually due to the inductive effect. So the way they minimize it, of course, they do this arrangement where the test loop is placed here, and then they connect the thin disk. The thin disk is to represent for the divider, but connect it in series. So they have this in series, and then and then this is another divider. They connect it in parallel, so that one divider connect in series S, and divider here connect it in parallel. So we call it, define it as P. Then they compare. So this is what we call calibration test. Calibration means you want to see which measuring device is better, accurate, or more superior than the other device. So in this case, you can see that this is the parallel, similar to what you've seen before, which is has the spike. But when you have the series, then there is no spike. It means that the inductive effect can be reduced even further. So this not only happens at low voltage, but also at high voltage. So you can see the author here, Professor Haddad, he put at low voltage and even at higher voltage. So at low voltage, so there's no spike throughout when you connect it in series. But this is just for sharing. I mean, but as generally, we know that when we do the measurement, especially the high voltage and high current measurement, then we are actually the inductive effect actually can be present in our test circuit, which will give different results than what really actually appear to be for the test loop. Okay, so this is one way to reduce the inductive effect. But as I mentioned, that this is more for the research purposes, but the common one is the second slide that I mentioned before. So now we know that we know the challenges in the testing and in the measurement. So now we see what are other challenges in this measuring device, and also to understand and to know what are the measuring device that are used to measure for the DC, AC, and impulse. So one typical method is the sphere gaps. Okay, so you can see here, this is the sphere, and then the gap here, and then so this is again the resonant transformer. Okay, resonant transformer, and then apply directly to this test. Sorry, not test loop. Without the test loop. So it means that if we see this circuit, just let me remove all this. Sorry. So let me go back to this one here. Okay, so if you see this Okay, so now my pen is ready. Okay, I think I'm glad that I got my pen now just now. Just a minute. It take a while. Okay, it looks like every page I have to edit this. Sorry everyone. Okay. Okay, so I just draw here. Let's see. Still not able to. Just a minute. Let me go back. Otherwise, I use my mouse again. Okay, just a minute. Just bear with me for a while. I try really to get. So it means that I can only use the mouse. It's okay. All right. So actually, I want to show that this when we do the measurement, you can actually especially if you want to know how we do this, whether accurate or not. So before we put the test loop, you can remove this part. You can remove this part. Okay. So directly from impulse generator direct to voltage divider. So what actually this diagram shows is exactly that, which is you have this resonance transformer. I think that you've covered this in the generating of high voltage. Okay, resonance transformer. And then this is directly to the measuring device without any loop here. You can see here there's no loop. And then if you want to do calibration, you can also connect it to the capacitive divider just besides this. So you have two measurement of voltage, one from the spark gap and then another from the capacitive divider here. But anyway, first we try to understand what is the sphere gap. So the sphere gap is used to measure for the DC. It can be used for all voltage types, DC, AC, and impulse. And it can also be measured for both positive and both polarities. But you will see later on the disadvantage of the sphere gap is that it's very much affected by the polarity. So for example, if I want to measure at 30 kV, at 30 kV, 30 kV here, positive. And then maybe at 30 kV, it causes breakdown. But if I were to measure under negative, I have to use higher voltage. So the reading will give you different readings. So if you apply, okay, I'll just go back just to make sure that you hope that you understand this. For example, you put impulse and then you apply 10 kV to 100 kV, okay, 200 kV, 200 kV. So you apply positives and then you plot this. This is a voltage from this impulse generator. So 10, 200, 100 and so on. But the voltage that appear under positive like this is positive. Okay, but you can see that the reading appear under negative will be slightly higher. Because there's it relies on the air breakdown. In other words, the breakdown voltage, the breakdown between this gap here. So this gap is of course like the air, and very much we know that for the air breakdown also can be influenced by the impulse polarity. So that's why here it says that it can measure for both impulse polarities, but later you will find that the disadvantage of the sphere gap is that it is very much affected by the polarity, as what you've seen here. You apply the same voltage 10, but when you measure at positive, you will find that the voltage reading lower than the negative, even though you apply the same voltage level. So I think this one you learn more when you come to the breakdown in dielectric materials. Okay. Okay, so two identical metallic spheres. Okay, this is the structure, or that you have two identical. It has to be identical, and then the gap length is normally less than sphere radius. So if your sphere radius is 100 cm, if your diameter is 100 cm, the radius is 50 cm. So the gap here must be much smaller, the line here, or the distance. Okay, so principles is that if a voltage with peak value is applied across the two spherical electrodes and the voltage is increased, or the distance between the electrode is decreased until breakdown occur. So when we apply, for example, 150 kV, then of course we have to adjust this gap that should give breakdown at close to that 150 kV. All right, so because we can see here that the equation is direct forward, that the V equals to E multiply S here, where S is the distance between the spark gap, and E is the here is the static breakdown strength of air, or in other words, the electric field, or the typical breakdown voltage of the air, which is normally we use it as 30 kV per cm. 30 kV per cm. This is the typical breakdown voltage of the air. And S is the minimum electrode separation. So it means that you have to adjust S accordingly when you do the measurement of different voltage range. If you do 100 kV, maybe the distance is smaller. But if you do the voltage is increased, like for example, if you have like 150, then the distance should be higher. So you can see that relation, which I will explain. I think I have the graph here later on. That you can see here that when you want to measure the voltage of 150, you have to increase the distance between the spark gap. Okay, so for higher voltage, if you want to measure for higher voltage, then the distance would be higher as well. Okay, so the condition or the specification of the spark gap, or the sphere gap here, is a smooth surface free from dust and grease and moisture. So you can see the construction here, it has to be smooth. It should not be dented, because when you have dented, then for example, you have the ball, it should be like this, but then because you have dented, so this dented will give you different electric field. So when it is a curvature, then the electric field will be smooth here, or in other words, uniform. But when you have dented, then the electric field will be distorted here. Will be, very much distorted. That can, of course, give high electric field at this point. Therefore, your measurement will not be accurate anymore, because you can see here that from this graph, you can see here, for example, we follow this reading for 250 mm diameter. So, for 250 mm diameter here. But if it get dented, then you may see actually that when you do the test, it may be like this, lower. It means that your voltage will actually break down even at lower voltage. Whereas you expect when you adjust the 50 cm, you expect the breakdown within 150. But you will find that the breakdown even occur at much lower voltage, because as I mentioned, that you have the dented, so the electric field is not uniform anymore. Whereas when you have uniform, it should be like this. my drawing. So it should be uniform. It should not be distorted, the electric field. So these are the um, that's why it should be smooth, and also from dust. It should not have dust here, because when you have dust, trapped in here or accumulated on the surface, then again it will give different electric field, not a uniform electric field distribution anymore. Okay, so I think that some maybe if you are familiar with the finite element, then you can see that the electric field when you have the uniform surface and non-uniform surface. So it should have a uniform curvature, okay, and should have uniform electric field between the electrodes. The radius depends on the separation, which in turn depends upon the voltage to be measured. So this is coming back to this graph here, where it depends on the voltage you want to measure. If you want 250, maybe if you have 250 mm diameter, then you can adjust it at 60 cm or within that range. If you wish, 450, then you have to adjust accordingly. And then we have a horizontal arrangement for smaller sphere. So it means like horizontal, it means like you have like this. Or you may also have vertical arrangement with larger surface or larger area here, like this one here. This is vertical arrangement. So horizontal, because you have like the arrangement is in such like horizontal. So it should be of smaller, because if it is too big, then this handle or shank here will not be, a lot of adjustment have to be done. It means that it may not have good strength to support this big sphere horizontally. But when you want to arrange for vertical, this can be larger size, because even though it's heavy, it can be supported vertically, because one is on the ground and you just have to support this one only, connected directly. Of course, this should have the structure to support it. And then there's a wire coming from, or cable coming from the resonant transformer here. Sorry. Okay, so the shank, as I mentioned, that should be free of sharp point. So if you have like this, and then this is the shank or the support, and then it should be free. You should not have like welding or like a large volume of welding or the big screw, because otherwise it can change the electric field around this. And of course, we also influence to the part, to the whole electric field distribution. So if you have like here, it will be like this. So it's not a uniform electric field distribution. So distance of sparking point from any conductive distance, we use the formula should be more than 25 plus V over 3, where V is in kV and V is the voltage to be applied. For example, if you have 25 and then you use 100 kV, you inject 100 kV. So 100 divided by 3 is 33 plus 25. So it becomes how much? 58, right? Yeah, so the distance should be 58 cm. It means that, if I go back here, it means that this is you apply 100 kV from the resonant transformer here. So you should have at least 58. So at least 60 cm, 60 cm here from the ground and 60 cm from this surrounding. So it means that you should make the radius of 60 cm from this spark or the sphere gap. Sorry, I keep saying spark gap, sphere gap. So that's the condition. So it gives clearance 25 plus V over 3. So this clearance actually different from one equipment to another. So that's why in high voltage, sometimes they use a common clearance. It means that um, why we need this clearance first of all. You know that the breakdown, if we take ideally, the breakdown is 30 kV per cm. Yeah. So it means that if you apply 30 kV, for example, you have the sphere gap of 30 kV, and then you have 1 cm here, and then it will break down. But if you apply 20 kV and this is 1 cm, this will not cause spark between the plate here. So it means that if we apply it in the high voltage testing, or in any, like if you go to the substation, high voltage, so that's why they put the equipment far from one to another, because they use this clearance, or in other words, distance of sparking point. So if I put one equipment here, 30 kV, and then I apply 30 kV, so the person have to stay at least 1 cm away. But of course lah, this 30 kV per cm is the breakdown of air for the considerably as ideal condition. But in reality, we know that because of the different atmospheric condition, different temperature, humidity, all this, therefore this 30 kV per cm not normally used in the when we determine the distance of sparking point. So it means that normally they use like this lah. Like for example, this one here, 25 plus V/3. So it means that if you apply 100 kV, if you use this formula 100 kV, you just only have to be 30 cm away, isn't it? Because 100 divided by 30 kV per 1 cm. So if 100 kV, then it's only how much? 3 cm. So that's why this is not applicable to, this is just for the ideal condition, for the breakdown of air. So the distance of sparking point is the safety or clearance distance to be away from the equipment injected, the equipment that is being injected. So we normally use this formula, like for this is actually for the sphere gap. But for other equipment, they may also have other way to or other formula to calculate it. But for the high voltage lab that we have at MMU, we use the common, in other words, we just take 2 kV per cm for all equipment. And sometimes if you're not sure, then because otherwise we have to calculate for every equipment. So we use 2 kV per cm. But if the equipment always cause sparking and so on, then we use 1 kV per cm or even lower, 0.5 kV per cm. So if I apply 100 kV, means the person or the equipment, other equipment has to be 50 cm away. But this one is even more actually. Like they use 25 plus V/3. If you apply 100 kV, it means the person or the equipment have to be at least 58, or in other words, round up to 60 centimeter. It means the person have to be away from the equipment 60 cm from the equipment under test. This one. So if I apply 100, so the clearance from the ground, the clearance from the surrounding would have to be 60 cm, at least 60 cm away. So you can see lah, it's around that actually. So this is how we determine the distance for the sparking point for the sphere gap. But for other equipment have different formula. But as I mentioned that for our high voltage lab, this is what we normally use, 2 kV, or if equipment is more dangerous, looks like prone to spike or flashover, that one we even use lower, like 1 kV or 0.5 kV per cm. Okay, so the typical material used, you can see here, these are the typical, but the one that you've seen in the example just now is brass or copper. Sorry. Okay, so this is the construction of it. It means that you have this horizontal arrangement and you also have the vertical arrangement, and then S is the distance between the spark gap, and D is the diameter of the spherical electrode, and A is the distance, you mean the clearance, the distance of the HV electrode from the ground, and B is the distance from the nearby object. So how we determine this distance, as I mentioned, that you can use this one here, 25 plus V over 3. So if you apply 150 kV, so 150 divided by 3 is 50. So it means that plus 25, 75 cm. The person or equipment have to be at least 25 cm. 75 cm if you apply 150 kV. So this is given in the standard. I mean, of course, if you do not have the copy of the standard, you can apply that formula just now. But as I mentioned, that different equipment would have different safe distance or the sparking distance, they call it. Okay, this is the design. Like if you have like 7D, value of A for S less than 0.5 D. So up to 25 cm for the diameter, then the minimum is 7D. So you can see that the diameter here is actually defined already in this diagram here. But this one is just to show that in the standard they give this guide that the high voltage lab engineer can consider. Okay, so other than that, this is also based on one paper, journal paper published I think some years ago, or many years ago actually, about the distance. The distance have to be adjusted if you wish to provide some guidelines, like if you want to have 100 to measure 150 kV, and then you have this 250 mm diameter, then you have to adjust the gap to this distance. So they make a few designs for the 100 mm, 150, and so you can see here the larger the diameter, the wider range, and steadily it can measure more steadily compared to when you have like smaller diameter, or when you have like sharp point here, like needle points. Needle point, it means like it's just like this. So you can see here the smaller, then is less steady. Excuse me, it's less steadier than the one with the bigger diameter. So of course, you can say that the larger, it gives wider range, and the voltage, the gap can be changed, more uniformly compared to when you have sharp point or smaller diameter here. So the factors influencing the measurement using sphere gap. Okay, one is the Earth object. When the gap is near the Earth object, the breakdown voltage reduces. So it means that when you have this, spark gap, and then you put the distance from the ground is shorter, then the breakdown voltage that you expect to have to occur, because you apply 150, of course you expect to have 150 kV here as well, but it may actually break down at lower voltage. It may occur at 130 kV. So this is very much influenced by the Earth object, not only from the ground but also from the surrounding. Like, in other words, if you refer to this diagram, it also influenced by this sparking point lah. It means that by this B here, the distance from the B. So if you, because you have to fulfill the requirement, which is 25 plus V over 3 as what you've seen before. But if you do not fulfill this, and then you put, or somebody standing here, or there's a nearby equipment here, very near, that not fulfilling that formula or requirement, then you may see that the voltage here will not be accurate. That it will give you the breakdown at lower voltage. So this is disadvantage lah. It means because it's very much influenced by other factor. And then next, when a dust particle is floating between the gap, so you may have dust. Okay, so dust around it, or even on the surface, moisture and so on. Then it results in erratic breakdown. So it's a heavy loud bang or high flashover from this equipment or from this field gap.
Doctor,
yes.
Sorry, stop here. Actually, refer to the horizontal. What is the voltage range meant by low voltage?
I do not have the range, but normally, if you, because you can see from this graph here that, for example, if you have larger diameter, you can of course measure it at higher voltage, but smaller diameter, lower voltage. But I do not have the range. I do not have the range what is the lower. But if you wish to go for high voltage, then that is the arrangement, because it's very much depends on the how well the shank can support that diameter. It's more towards the what they call towards the construction or the structure. Is in terms of you know, as long as it can hold, normally it should be all right. But if the heavier, then it has to be constructed, and the heavier is because of the size. So I think the concern is how heavy instead of what's the voltage. Because different material would have different weight as well. Like aluminium, maybe, you know, I am not sure. I think it's more towards the heaviness rather than the dimension, the voltage level. But I'm not sure. I do not have the range for that.
Okay.
Okay, so another is the dust particle and atmospheric condition. Okay, this one we know that we have to correct it according to the standard. And then irradiation, where illumination of sphere gap is. So there are some techniques that are also used, such as with ultraviolet or X-ray aids, which is to allow the breakdown happen directly from one end to another end here. So the effect of irradiation is pronounced for small gap. But if you have very small gap, for example, if you see here that small gap is very much affected by this irradiation or this technique to aid, which is used to aid the breakdown from one live conductor to the earth conductor. And then another is effect of polarity and waveform. So as I mentioned, that the polarity, positive and negative, have different characteristics. I think that maybe if you have come to the chapter breakdown, then you will see that the different characteristics for positive and negative. So for, as I mentioned, that if you put this voltage from the impulse generator, okay, from the impulse generator, if you do for the positive, for the impulse generator, for positive maybe for low. If this is 50, this is also 50. But for negative, actually it will give higher. So because it rely on the breakdown of the air. So this, I think you will learn in the at MMU we have this as another topic, which is breakdown in dielectric. Because you can see that your equipment sphere gap is very much dependent on the gap, which is the air. Air breakdown is influenced by the impulse polarity, which in general you should know that the negative polarity give or in other words require higher voltage to cause breakdown. For example, if I have the transformer breakdown or the withstand test, I'm not sure whether you cover the testing already in the in the syllabus, but for the withstand test, for example, for the transformer, maybe 75 kV for positive, plus is 75. But the withstand test for the negative will be higher. Maybe for negative, it would require only at 80 kV. 80 kV, it gives a breakdown. It means that the withstand test for the transformer, it gives 80 kV under negative. Because negative, in general, it gives less severe impact compared to the positive polarity. But this one, you will learn looking at the charges in the positive, negative, and so on in another topic, which is breakdown in dielectric. So that's why, because of the severity in positive, or in other words, the worst scenario is in the positive polarity. So that's why in many high voltage tests, they do just the positive, because once you get the results of the positive, you can say that, okay, this is the worst scenario. For negative, it gives less severe than a positive. That's general lah, but of course there are other through my experience that there are certain times that sometimes it gives similar characteristic, positive and negative. So those very much into, there are many other possibilities or statistical characteristic of the dielectric material as well. But anyway, we should know that the sphere gap, it gives the effect of polarity. So it is observed that the spark over voltages, front and tail time for negative and positive are different. So that's why the sphere gaps, when you test under positive, you will find that the result of negative can be different, even though you inject or you supply the voltage from the impulse generator or from the AC or DC source are the same. So another type is a uniform field electrode gap. I have to say that actually uniform field electrode gap is not widely used in high voltage equipment, high voltage lab. This is more like, I can say, towards the research lab. But anyway, we will just see in terms of this simple construction here, that the sphere gaps have only limited range with a uniform electric field, and the researchers have presented a design to produce uniform electric field to measure AC, DC, and impulse. For example, VB here is, this is how we calculate the breakdown voltage. Whereas just now for this sphere gap is direct forward, where V equals to E multiplied by S. But for the uniform field gap, the V is 24.22 plus 6.08, and the gap distance here is in square root kV for the atmospheric condition. So you can see here there's a flat surface here compared to when you have the sphere gap is very much round here and the round here. So advantages, so the advantages you can consider as the disadvantage of the sphere gap. The sphere gap we have seen that is influenced by nearby Earth object, but for the uniform field gap, it has no influence of nearby Earth object. And then the disadvantage of this sphere gap is the polarity. Yeah, so the disadvantage of this is no polarity effect. But of course, this equipment, which normally used for the actually mainly for the research, so very accurate mechanical finish of electrode required, because you can see that it has larger surface here. So you have to make sure that these are uniform, and have to make sure that this is aligned. Careful alignment. If this is at this point here, then it should be at this point here as well. So it has to be added correctly or arranged correctly with this construction of this uniform field electrode gap. So careful alignment, and then influence of dust. Of course, this one also influenced by the dust, because it has larger area. So you can see that this is more serious than in sphere gap, as the highly stressed electrode areas become much larger. So when you have the spark here, it can cause, of course, flashover here. And sometimes if this is too high, it can also, of course, not only, it means that it is possible to affect the test loop. For example, if you have the test loop nearby, transformer or other equipment, but if this is too large, that flashover, you can imagine it as, because flashover in the term that you learn normally in the testing or the definition of all these terms used in high voltage. So the flashover is the normally like the sparking similar to lightning. So you can imagine that if there is a equipment nearby, then it may also be give influence to those equipment. Okay, so thus a uniform field gap is normally not used for voltage measurement. So if you go to many high voltage lab, they have this sphere gap, and like and voltage divider, and the list that I've shared earlier, such as the electrostatic voltmeter, generating voltmeter, and so on. Okay, so the last one is the voltage divider. Okay, so voltage divider I used to reduce the high voltage to a lower level, obviously. So it means that you measure how much? 100 kV, right? So this voltage divider, surely you need the oscilloscope or DSO, digital storage oscilloscope. All right, digital storage oscilloscope. So if you apply 100 kV, so I go back to this diagram here so that I can show you. This is voltage here to the oscilloscope. So if you apply 100 kV here, of course you cannot let this 100 kV to go to the oscilloscope, isn't it? Because it can, of course, damage the oscilloscope, digital storage oscilloscope. So it has to lower this voltage 100 kV to the value that can be measured by oscilloscope. How much is the maximum voltage that can be measured by the oscilloscope? You've learned this one, right? This is oscilloscope. How many division you have? 10, 8, 10, right? And then what is the maximum voltage per division? You have the, what they call the knob here that you can see. What is it? So 10 division times with, sorry, my writing, so sorry about this. Times with, what is the maximum voltage per division? 5 volt, right? Digital nowadays. 5 volt per division. So what is the voltage that can be measured here? 10 volt times 5 volt per division, so it becomes 50 volts. So you can only measure with the oscilloscope of 50 volt. So you have to bring this 100 kV to only 50 volts. So that's why they use the voltage divider. So here voltage divider to reduce the high voltage to lower value so that it can be measured using the DSO. So we've seen the example just now, 100 kV to be measured with 50 volts of DSO. So voltage dividers for AC, DC or impulse voltages may consist of resistor, capacitor or combination. So that's why they call it capacitive divider or resistive divider, and another is they call it as RC or resistive capacitive divider. So inductors are not normally used because we've seen that inductors considered as or in other words the culprit that can give you oscillation. And then in fact you try, the studies have shown that we try in many ways to minimize this inductive effect. Because first, we do not use inductor because pure inductors without stray capacitance cannot be built. That's one thing. And then another is inductors would form oscillatory circuit. So what I've shown before, instead of having this fast rise time, then you may have the oscillation on the circuit or in the response. So inductors with the inherent capacitance, where capacitance, we know that the equipment should all be represented by the capacitive load, like your cable, transformer. I know that you have learned maybe in in some subject before the equivalent circuit of the transformer consists of the resistance, leakage impedance or the magnetizing branch, but in the high voltage we only represent it as one capacitance here. So L with the C can give you the oscillation as what I've explained in the first few slides earlier. So this gives you the inaccuracy. So that's why the inductors are not used for the voltage dividing element. So the height of voltage divider depends upon the flashover voltage. So it depends upon, like, the higher the voltage, normally you would see that the higher it is from the ground, because this also need to provide the clearance. So in general, the principle is that the values of Z1 and Z2 are chosen such that the output voltage is a few hundreds or thousand volts. So it means that your V2 is the one that you measure at the DSO, and then this one is the voltage applied on the equipment. Like for example, 100 kV. 100 kV. So you have to make sure that this V2 should be measured by 50 volts only. So you have, and then V1 is depends. If you want to measure maximum of 100 kV, so it's 100 kV. So you have to get the value of Z1 plus Z2 divided by Z1 plus Z2 here into this equation, but give the value of the V2 very small. That should be able to be measured by the oscilloscope. So how much is it? Like for example, 50. What would be this ratio? This is not the ratio, is we take as V1 divided by V2. So it means that if this is 50, this is 100. So this should be 50 divided by 100 kV. So it will be it's very small value. Yeah. But if you want to consider as the ratio, so we take as the V1, sorry, it means that when you get the value, then you have to divide this value here to give you the real output. For example, if you obtain, so it means how much is not this not point, not 1, is it? What is it? When 50 divided by 100 kV, not point, not 5?
0005.
Yeah, not point, not 0005. Okay. So when you obtain this voltage at the oscilloscope, then you have to divide by this. Then you get the V1. How much actually the voltage actually real applied to the test load. Okay. So for resistive divider, then you just change lah this one with the R1 and then this is with the R2. For capacitive divider, because we know that capacitance, the impedance is represented as 1 over. So of course C1 and C2 as well. But when you change it to 1 over, rearrange the equation, then it becomes C1 over C1 plus C2. So this is the example of this resistive divider. This is actually the one that we have at our university that can measure a maximum of 300 kV. So this is, so the construction is that it has on the Z1, it has R1, many R1. We put it into several units. Of course, not me lah. I mean, the manufacturer, they put it into several units. There are reasons for that because we know that when you have bigger component, then the heat will be more, the losses and everything will be more, and this one is like general. We all know that instead of buying one unit, then they put it into several units. There are many advantages to that. So the resistive dividers are preferred for the measurement of steep impulse, impulse, and not only impulse, actually like AC and DC as well. So they divide it into small components for the R1, and then it has the R2 or this one here. So R2 can be on its own because of smaller value. So that's why its R2 is much smaller. So that's why it can just be one unit here. Sorry, this one I did not put it in here, but this one actually because of the stray capacitance. When you have the resistance, you also subjected your equipment to the stray capacitance and ground capacitance. This one cannot be, it means that when you have this resistance, then you are also subjected to the stray and ground capacitance, which cannot be avoided. But it can be minimized by having this guard ring. Guard ring is like you have actually capacitance all connected to one terminal point here. This is just part of the construction. So when you have this, then you can actually minimize the stray and ground capacitance. Because if you do not minimize this, then instead of having this ratio, you actually also have the CS, and you also have the and then you also have the stray ground capacitance and stray capacitance. So your ratio will not be the same anymore. Maybe you earlier calculate as 0.005, but now becomes other value. So when you try to include or couple it with your calculation, then this will not give the real reflection of the output. Why? Because you have the stray capacitance and ground capacitance. But of course, this is on the manufacturing part that they would have to consider this using the guard ring, so that this will become less pronounced, and the results can just be from this equation without including the stray and ground capacitance. But of course, as a user, like in our case, like for example, we have this. The first thing when this equipment arrives is we do the calibration. So calibration, as I mentioned, is easy. You just have to Sorry, I just have to go to the circuit so you understand what the calibration test means. I know that some of you may familiar already, but calibration is easy. Like, you know, you remove the test object, and then you just directly one capacitance here, sorry, one divider here and another divider here. And then after that, you connect, this is the voltage applied from the impulse generator. Then you can plot one from the voltage measuring device A, and another is voltage measuring device B. So that's how, and then we see which one actually is closer to the input voltage or the charging voltage. So that's the typical test that we do whenever we have the new equipment. Similarly, for the voltage divider, for the C1 is much smaller than C2. So of course, because C here we refer to 1 over. So of course the C1 now is divided into several sections or subdivided unit. And then you have the C2 similar to the resistive divider before, that the C1 that have several components, whereas C2, because of its large value, much larger than the C1, then it can maintain as the C2 component. Yeah. Okay. So this is the one we have at MMU. Normally we run the test by the field measurement. So that's why we have to bring this to the site and run the test at field site here. This is one of the site that we use inside campus actually at MMU. Okay, so all this, because just from this, you're not able to get the reading because it only has the circuit of capacitance, C1 and C2. So you have to connect it. The lower arm have to be connected to the oscilloscope. So from this oscilloscope, then you get the reading coming to represent for the test load. So this is the typical voltage captured on the DSO. This one actually I got from the internet, not my own reading. But anyway, you can see here that recorded for 1.2/50 to healthy insulator of 11 kV. So this is what they observe from the oscilloscope. So here it says that the voltage y-axis is 20 kV, 20 kV per division. So you have 20 to 468, around 210 here, whereas x-axis is 10 microsecond per division. And then this is also the response obtained with the divider. So, but this one is faulty. So you can see that when there is a faulty, there is a sudden drop in voltage. So, or voltage collapse, we call it. The voltage collapse to 0. So that's indication that the insulator failed. Okay, so these are the challenges in terms of the when you using the divider. Okay, divider. So the cable is terminated because you also have the oscilloscope. Okay, and the cable that connect from the divider to the oscilloscope also has its characteristic impedance. Yeah, the cable, like, you know, you have a 75 ohm, 50 ohm cable. So it has its own characteristic, or in other words, it has the characteristic impedance, which can become part of the circuit. So it means that when you have this ratio, but because this one you also connect to the cable and to the oscilloscope, so this equation may not be valid anymore because it has maybe to include the resistance of the cable or capacitance of the cable, especially for this one here, plus the C of the cable, capacitance of the cable. So when you have this parameter, then this calculation or this ratio may not be accurate. So this is the consideration. Of course, when the designer or when we buy this divider, we use this ratio. But when we do the measurement, the cable and everything is not, in other words, it's not a concern of the manufacturer anymore, because the manufacturer, they provide this one and they provide the ratio. But when we do the measurement, we may not use the same ratio as what they suggested, because it can be the case that our cable has its characteristic impedance. So that's why the calibration test is very important. But here I just want to highlight the characteristic impedance. When you have this, then it introduces another resistance. So as the coaxial cable is terminated, the step voltage is transmitted without distortion. So normally for the resistive divider, whatever appear is directly appear on the oscilloscope. But for the current measurement, that but I didn't also put it in the slides, but you may experience that for the current measurement, the current may be double. The current may be half appear on the oscilloscope. For example, the current is 10 kilo amp, but appear in the oscilloscope after you convert it, it become less than 10 kilo amp. So that can also happen because of the cable impedance characteristic. But it's not covered in this lecture, because that one I think we actually have or do it for the testing, which is another chapter at MMU. So to avoid traveling wave oscillation for the capacitive divider, normally resistance R equals to Z is connected in series with the cable. So capacitive divider normally is cable normally provided by the manufacturer, because in that cable they already consider this R equals to Z. Because at C2, which we know that is very large, the voltage across C2 is half. So it means that the voltage at the C2 is half. So when it appears on the oscilloscope, it will be half. But I'm not sure whether you have covered this part or not, that when you inject high voltage, for example, impulse or AC or DC, if I take the impulse here, maybe 1 per unit. But when it reach another end, then it will be times 2. Times 2. It means because of the reflected voltage. So this is actually used, I think, mainly in the protection systems, when it impinge, the high voltage impinge on the one termination, then it reflected back with a double, so 2V. So if you apply 100 kV, it reflected voltage will be 2 times 100, which is 200 kV. So it's the same thing here. So, but because of the manufacturer, normally it comes with the N cable of R equals to Z, which they included here. So the voltage appear at this oscilloscope will be half. But because the nature of the reflected voltage, which is times 2, so half times 2, then it will become 1. So that's why when we use the capacitive divider, what appear on the oscilloscope, we do not have to multiply or divide by 2 anymore. But same with the resistive divider, because we know, as what we've seen earlier, but for the current, high current, we may have to multiply by 2, because the voltage has been half due to the resistive load and due to the cable. But that one is another part that you should concern. But at this stage, you know that how we manage to get the voltage appear without multiplying or divide by 2 anymore for the capacitive divider, even though we know that the reflected wave by nature actually it should be 2 times of the impinge or the applied voltage. So here is the effect of the cable. So as you can see here, that the ratio normally we just obtain like this, but because of the presence of the cable, then this CC will be reduced. But the error as also become a concern to the manufacturer of the high voltage divider, that normally a capacitor in series with the resistor is can be considered. That's why we normally have different or the cable at both ends or terminal of the cable we supplied by the manufacturer, because they have this condition already. Okay, so the next one is a measurement of high current. Okay, so this one I just go very briefly, because high current, as I mentioned, that in high voltage lab, normally, or I can say majority, they use the high voltage. They hardly use high current, because high current you only have to, of course, to you only have to do for, just a minute, let me check again. Okay, you only have to, for circuit breaker, testing of circuit breaker, but circuit breaker, normally the manufacturer of circuit breaker have this, but anyway, okay, testing of circuit breaker, and then the resistive component, resistive load and grounding, and of course cables. But you can see that in comparison to the equipments I highlighted before, which is transformer, insulator, bushing, and all that, those using mainly the high voltage measurement. So that's why this high current is less popular. In fact, if you go to many high voltage lab in Malaysia itself, you will find that most equipments have the generating and measurement for the high voltage, not for the high current. So, but anyway, this still very much needed for this testing of circuit breaker and resistive load, where your load is the resistance, not the capacitance. I mean, it can be capacitance, but then not for the, there are certain tests that require the high current. Okay, so lightning discharges and switching transient and temporary over voltages, and typically installed in an electrical panel or switchgear, where this actually installed. So this current, they also put it in the substation or to the substation to obtain accurate reading in terms of energy and power measurement. So this one is example of the UI curve for the 550 kV network. So they still need this current measurement. And this is a example of the current measuring device installed in on the structure actually, for fixing and securing. The photo of the upper right here show the current measurement. So what happened is that they actually run the test to capture the lightning, for example, capture the lightning, and then in high tower, and then from that, then they be able to get this, place the current device in here, which have the cable connect to the normally control room or to the safer place, normally in a cabin or nearby cabin and so on. But nowadays, with the recent technology, they can actually monitor it remotely. So one method of measurement is resistive shunt, because of its large dimension, will have residual inductance and capacitance. So resistive shunt, it means that you should only have the resistance, and the range of resistance is 10 microohm to a few milliamp. So again, you want to measure this current. If I just go back to this circuit, the first circuit that you see with the this one here. Sorry, this one here. So this is current shunt, and then this also to the oscilloscope. Yes. So if you apply the voltage, and zinc oxide is a resistive load. Resistive load. sorry, not capacitance. Okay, the resistive load. And then, so the voltage appear here, divide by the resistance of the zinc oxide arrestor, then give you the current, then the current here appear on the oscilloscope. And we know that the maximum current, sorry, the maximum voltage can be measured because the oscilloscope is in voltage, not in current. So 50 volt, 50 volt, right? 50 volt voltage, maximum voltage to be measured. So, for example, this you apply 100 kV, okay, 100 kV to zinc oxide arrestor, of course non-linear, but for example, the resistance is 1 kV, so the voltage, sorry, the current should be 100 amp, right? 100 amp. So 100 amp, you have to get the resistance very small so that it can be captured by this oscilloscope. So 100 amp, maybe the current shunt can be, because the current shunt can be maybe, current shunt means the resistance. The resistance can be maybe 0.1 ohm or volt per amp. So normally it's a volt per amp, or in other words, 0.1 ohm. So it means that for every 0.1 amp, for 0.1 volt, 0.1 volt, it gives 1 amp. It gives 1 amp. So if you have this, how much is it just now? 100 kV divided by 1 kilo amp, so it gives 100 amp, right? So 100 amp. So 100 divided by 1 times 10, so it should appear on the oscilloscope as 10 volt only. Yeah. So this is the, that's why the current shunt must be very small. Or in other words, we call it, yeah, it says the current shunt, but sometimes we call it as the resistive shunt. Okay, so this 10 microohm to a few milliohms. It can also be just a few ohms. The value of the resistance is determined by the thermal capacity and heat dissipation. So there are a few types, such as to reduce the stray C and L. This is more in terms of the construction of the resistive shunt. Okay, so they have different types. One is bifilar design. So just wound in opposite direction. So this is just, basically you can say that this is resistance. This is resistance. The challenging part is to produce it very small value, like in 10 microohm to a few milliohm. That is just the challenging part. So how they use it, actually they use sometimes the insulating spacer, Teflon or bakelite for the insulation, and then the metal base they use, that as long as it can give you the value of a small resistance value. You need it small because the voltage is 100 kilovolt apply on the test load, and then you have to make sure that the 100 kilo amp, for example, captured on the oscilloscope and safe to be captured by the oscilloscope, which is the range, you know, the range, the maximum voltage is, in terms of voltage, is 50 volt. So you have to make sure that the current that from 100 kilo amp is very much, reduced to, should be below 50 volt, the one that can be captured by the oscilloscope. So this is this is just in terms of the design, where again to reduce the inductive effect, and the method is called the coaxial tube, which is actually, it's like a cylinder. It's like a cylinder here. You can see that and then this is the input, and this is the, sorry, here is the input where you have the coaxial, and then another is the output. Because as you can see from the circuit, that it should be one is from the live here, and from, of course, from the to the load, and out of the load to the resistive shunt or current shunt here, and then another is to the ground. So the same thing, the way we construct it, where when you have this design, it should be one is from the live and another is to the ground. So just that the because this is, as I mentioned, is to the for the research. So this is mainly like for the research, like you can see the material use have to be like just now we use the Teflon or other metal base, or other quality insulation. And this one here is the shape, it has to be coaxial so that you can reduce the inductive effect. So and then the voltage across the resistive shunt element is measured between the potential pickup point and the outer space. So you can imagine that your circuit is, for example, this is, for example, you have the circuit, this is the transformer. It's like you put just one resistor here, just that. So the resistor, of course, you have to make sure it has high thermal capability, it is not influenced by the inductance, but this is component, the main component must be resistance, and the value must be very low so that it can be captured by the oscilloscope. But generally this is the resistance. So the design, it can be like, you know, of course they make it coaxial because they want to reduce from straight inductive effect, and the material must be carefully selected that has high thermal capability, and then doesn't have inductive effect in terms of the structure or the design, and then able to give very low value. So that is the consideration when we want to measure high current. But that is resistive shunt. Another, okay, this is also again another type of resistive shunt, which is using coaxial squirrel cage. Okay, and this one you can see the shape is a coaxial, again for the purpose to reduce the inductive effect. But this is mainly like used for the arc current measurement, because normally arc current here, when we say arc, it means it refers to like flashover or sparking, which can be very high value, very high value. So because of this, then high ohmic value shunts normally used, because previously we've seen that the ohmic value should be very low, because otherwise how you're going to capture the 10 kilo ohm on the oscilloscope. So that's why the ohmic value has to be very low. But in this case, when you want to measure for the extreme current, highly or extremely high current, then you have to use the high ohmic value. So because of that, then the tubular shunt may not be suitable. Then the coaxial squirrel cage can be used, replaced for that by thick rods or strips resembling the rod to construction here. All right. So, but anyway, this is more like for, in other words, general information, the typical resistive shunt. But the more common one is the Rogowski core, where it is measuring AC or impulse, does not have a metal core. This is not metal core. This is just a winding, toroidal winding of copper wire wrapped around a non-magnetic iron core. So this is your cable, for example, and then you have this toroidal core, and then it induces the voltage, and therefore we know that the current is proportional to the voltage, then it gives the current reading. So if the current to be measured is flow through the conductor here, which is surrounded, and M is the the mutual inductance, the voltage across will be M di over dt here. And then this the design will have to consider the number of turns, the cross-sectional area of the coil and L, and then it gives you the mutual inductance M is given as this, which later can be used to calculate for the current, where the current is proportional to this output voltage. Okay, so this is just the some examples of the Rogowski coil. Another type is current transformer. It's slightly different than Rogowski coil, because Rogowski coil, you can see here, it doesn't use the metal core, but for the current transformer, it uses the metal core here, so or magnetic core here. So the current transformer, a steel core is used. Then it will create magnetic field. Then current transformer reduce high current to a much lower value. And then this also have a few winding, a few turns as its primary. So the equation is that the N, or the ratio here, is IS divided by IP. So secondary current, which is should appear on your oscilloscope, should be IP multiplied by the ratio of the primary and secondary. So the common device that we use at MMU is this current transformer. But the the sensitivity, we call it, is normally 0.01 volt per amp. And then this is for higher current, but for lower current, we can use 0.1 volt per amp. So if you want to measure, it depends on the current measurement that you want to have. If the current is more than 1 kilo amp, then normally we use this one. If the current is less, then we use this one. So it also comes in different range. So this is the one that we connect at MMU, where you can see here the black is the insulator, because we do not want to have flashover from this metal current transformer to the cable, because we have this cable here. So this hollow insulator is to avoid basically flashover, because you have to put the current cable across this hole here, or sorry, through the hole here. So you can see here, but in some cases it can cause flashover between this metal core and the cable. So for that reason, we have this insulator, epoxy insulator, hollow, and then we put the current transformer, and still the current can go and still induce and obtain or produce the output voltage. So this is just to share the current transformer when we have the calibration actually. So we have two current transformer, and we calibrate. One is producing very high oscillation, whereas the other is more steady and without oscillation. So in our selection, we have used CT1 throughout our measurement. Okay, the last one, which is partial discharge, as I mentioned before that. Anyway, we come to the end already. So I'll just go very briefly in a way that, just to expose you what the partial discharge is. But I think because at MMU, we put this topic under the testing. Like for example, you can say that you have done all the connection in the substation. Then how do you know that your connection of the cable and everything is intact according to the standard? Because you have to rely on your staff or your worker. So when everything is done, then normally we apply this partial discharge measurement, so that we'll be able to know the health of whether it passed the test or not. So this is part of the testing requirement. So here PD are partial. It means that partial discharge, it means that when we switch on in partial discharge, it means that only partly of the insulation has void or has flaw. For some cases under high voltage, then this can be easily faulty, right? Or it may not be faulty. Only after some time or only after very high voltage, it can cause fault in the systems. But in general, you should know, because as the term itself is partial, so it's partially, in other words, part of the insulation only is breach, or in other words, have a flaw. So in this case, like in fact, the term used is localized electrical discharge that only partially breach the insulation. So it's not enough. For example, you may have like void here, but if a full discharge, maybe it's like this, like crack all the way. So that maybe can be considered as full discharge, but here is only partially discharged. So normally when we see that how, whether it's still healthy or how long more this cable can last and so on. So purpose is to identify the types. So from the types, then we'll be able to correct the particular parts responsible for this partial discharge, and then determine the origin and detect the flaw in the equipment. So this is example when you have some partial discharge earlier, but when after the test, then it causes, means that we know that this must be the problem in the cable termination earlier. So there are a few methods: electrical, acoustic, optical, and electrical. So this is the common one, the electrical. So as I mentioned before, that I will just go very briefly. This is for laboratory measurement, and this is the typical offline, and this is online, which can be remotely monitored. So, and then the partial discharge, it actually has voids, and then once we run the test, then we'll be able to diagnose as well whether it's due to different types of partial discharge, such as whether it is cavity, corona, tring, and surface discharge. Okay. So I think that be all from me. Sorry, I think that I have extended 10 minutes from the original time. So you are welcome to ask me a question. So just to share with you, this is the testing that we run in China with the China Electric Company on the impulse generator. So you can see this one is 1,500 kilovolt. Sorry, 15 megavolt, 15 megavolt, and the current is 100 kilo amp.
Is that the one that you bought for MMU?
No, that one, this is too expensive. We can't afford it for now.
So for MMU, how much you can
For MMU is only 300 kV and 10 kilo amp.
Impulse, yeah?
Impulse. And we have another mini, what we call it as a smaller one, which is 100 kV and 1.5 kilo amp.
1.5 kilo amp.
Enough to play around, yes.
Okay, thank you very much, Prof.
Thank you.
Normiza. So, and also thank you everyone for staying engaged. Hopefully tak tidur so please ask if you have any question, especially those yang sekarang ni tengah buat project, final project, master project kan. So take this opportunity to ask the expert. As you can see just now, ada many methods kan, such as untuk measure voltages, currents kan. Also saya tahulah yang banyak buat FYP pun ada tentang partial discharge kan. So maybe you would like to ask question to Prof. Normiza, please ask. Boleh raise hand dan saya panggil lah nama tu, siapa nak tanya tu. Ataupun kalau you malu, you boleh tulis kat chat box, nanti saya baca dekat Dr. Normiza. Malu ke? Sila.
Feel free to ask. I'm not so much of knowledge into this as well. I would like to learn from you, like, what Is it that because sometimes people meeting the e-shop sendiri, like, you've been doing tests here and there, but have you really consider, like, what are the concern, or from the public or things like that? That would be good to see that as well.
That I personally think that before this student kita lah kan, dia buat lab, dia pernah buat lab, dia pernah buat measurement maybe during electric circuit courses dekat tahun 1 tahun 2 where they construct circuit, measure voltage and current, apply Ohm's law and so on. But during that time, when they measure, they can measure directly, right, from the circuit to the voltmeter ke apa ke, apalah yang dia boleh measure tu kan, measuring device tu. But now, as you can see on the lecture slide just now, for high voltage, bila dah pergi masuk sistem yang high voltage ni, the measurement tu memang very much different lah from what we did during yang
More
smaller
influence, yes.
voltage punya level kan. Kita perlu ada divider lah, voltage divider, resistive divider and so on. So that is one significant different lah yang kita boleh nampak. Maybe yang tu lah, saya nampak tadi pun all techniques tu dia punya principle, the basic principle is the divider tu kan. Kita nak make sure whatever we measure tu can be captured safely at the measuring device yang kita nak dapat. Yang tu that is the most important point kan, measuring device tu. No matter how good we set up all the circuit tu to measure, but kalau tak boleh capture dekat measuring device tu, no point juga.
Yes.
Right?
Yeah. And then when you able to measure it, also you have to see whether the source is really from the output of the test loop or from other testing arrangement. That's how you set up
the test measurement.
That's also another factor.
Anyone ada question ke? Kalau tak ada, saya tanyalah. Untuk partial discharge tadi kita nampak kan, dia sekarang ni ada macam inilah bukan partial discharge sajalah, yang lain-lain pun ada banyak choice lah kan. Contoh kalau kita nak buat nak measure current tadi, ada Rogowski, ada current transformer, ada shunt. So which one, how do we select, how do we choose which techniques to use?
Actually, like for example, if I just take the simple example lah, between the voltage, you have three methods here: sphere gap, uniform field gap, and
voltage
divider. Not to mention those electrostatic generating voltmeter and so on. They have advantage and disadvantage. But for example, the sphere gaps highly used back then, but sometimes in terms of the what they call adjusting the gap, or like because of influence of the polarity, especially when you want to study dielectric material, you want to consider the polarity effect, and yet your measuring device itself give the polarity effect. So because of that, in my case, I tend to rule out this gap. And then, as I mentioned, for the second method is the uniform field gap, is more like for the research purposes, because it also require the alignment, the correct alignment and so on. And especially for the university, we let the PhD student or master student to handle this, and it's not that we are not confident in them, but at the same time, they may miss out what they call the training done by the previous student, whereas they join another batch and another batch where it can be different group of students and so on. So in my selection, I avoid that as well. So in the end, I come to the voltage divider. But of course, like electrostatic voltmeter, it has a big advantage as well, but sometimes it can be
accuracy problem.
Yes, accuracy, too sensitive, especially when we do like field testing in our application now. And of course, like generating voltmeter, it uses the synchronous motor. And it's Corona's motto, you need another switch to plug in and so on. Whereas, depends, like all this, and it can be, you may have to attach to the maintenance or to the supplier to keep maintaining your equipment because you have the motto.
Right.
So there are many ways, but of course, in the end, it also comes to the budget.
Of course.
So, so and then what you most familiar of, and then what you trust on, and of course, like even though we say that voltage divider, it also has like different manufacturer, but, and of course, we also know from the market which one is more reliable than the other, and so on.
Right.
But those again come to our little tiny budget that we have. So we got this one, something like that.
Okay. Anyone other question?
It's not purely technical lah. It's not purely technical. It's more like how you logistically, how you uh,
How accurate you want the measurement to be.
cater it to the benefit of your students, easy for them as well, and how skilled they are, or it's just more like typical workmanship that they have. So
Right.
it's very much depend on that as well.
If it is too complicated to set up, then that will be a problem too, right?
Yes, correct.
There is question dalam chat box. The mutual inductance M is a critical parameter in the operation of Rogowski coil. How to optimize that M?
Yeah, I think M is very much influenced by the inductance, isn't it? So one way is of course like to how you wind it. That's one thing. How in terms of this design lah, but you're referring to the the Rogowski
Of the
coil only.
Rogowski.
So how you wind it, how the number of
Conductor
winding.
use.
Yes, conductor use, yes. But for this circuit, for example, the first one that we've seen before is how you reduce the mutual inductance is in terms of the looping, like make it close, but at the same time you have to consider the sparking distance and so on, the physical size. So it's more like that.
Okay. Any more question? No. How to identify? There is another question. How to identify the type of PD from the testing results we get?
Actually, this one I just put very brief, but this one actually you get from the display, like the PD display, especially when you run it in the lab. It's not like necessarily from the oscilloscope. But if the oscilloscope, for example, you manage to capture the current or the voltage, you can see oscillation. Oscillation means that throughout the waveform. So that's likely that you have the PD, because we know that the PD is enough to cause the corona or the disturbance, but not enough. The electric field is not high enough to cause full breakdown. Because if full breakdown is easy, you can just see the collapse of voltage, like what you've seen. Where is it that I show the sample? Here. Here, the collapse of voltage means the full breakdown. But for the
Partially charged.
PD, partially discharged, is not like this. For example, when you apply, it still can maintain the similar impulse, but maybe with some oscillation. But when you have the display, those are the reading from the oscilloscope. But if you have the display, it gives you in the display this kind of charges. That whether it is just here or the accumulated here. So this actually tell you in other words, it diagnose whether it's surface discharge, cavity, string, so that. But of course, that you would have to look at into detail. I also have these slides, the example from this website here that you can refer to. But of course, if you get into different material, and then so it means like it's more like towards research lah. But
classification, yeah.
Yeah, classification. Yes. and identification based on the signals you receive.
Signal. Okay, I think tak ada takut. Ada soalan lagi? Anak-anak kan dah tidur semua ni, cuti kan? Okay.
Soalan kot last lah.
Okay, Syukri. Sila.
Berkaitan dengan partial research. Saya
Partial
ada
research.
buat untuk research. So basically saya ada baca few paper kan. So, untuk offline test partial research ni, kita akan gunakan coupling capacitor as dia punya medium untuk kita measure PD. So saya ada tengok few tu dia menggunakan kapasitor yang berbeza dari segi farad dia tu. Ada yang pakai 80 picofarad, ada yang pakai 1 nanofarad, ada yang pakai 2. So apa dia punya significant dan apa dia punya difference dia sebenarnya in term of kita gunakan a different coupling capacitor, impact dekat result tu macam mana?
Alright. What is the purpose of coupling capacitor, if I may ask you?
Untuk kita ambil measurement PD tu lah. So
To
basically
isolate.
kita nak
Basically you want to isolate, right? Isolate the maybe healthy one to not healthy one, and to isolate the high voltage, low voltage, things like that. That is basically the purpose of the coupling capacitor.
I think so.
So the one that you have is different value. I'm not sure exactly because my research is not really into that, but I think it's more like accuracy lah. In terms of like, you know, how well you able to isolate one signal from another signal. I think it's more towards that. But I'm not sure. Maybe in the paper they show the characteristic as well when they have different values used. So maybe that answer the question lah, in what way it contribute. So I'm not sure exactly why different, but I know the main purpose of coupling capacitor is to isolate
the
one signal from another.
So maybe
sebab saya pun confused jugalah macam mana nak interpret benda ni kan, sebab ada standard IEC tu sendiri dia kata the best is 1 nanofarad, but then kita tengok ada yang in industri dia ada pakai 80 picofarad. I don't know, maybe in term of costing ke apa, yang tu kita tak pasti.
Different signal requires different value lah kan, kalau dia nak tengok.
Maybe.
Yes. And then you use the partial discharge monitor, or you use based on the voltage and current signal. Which one you use this detector?
Kita pakai voltage and current punya ni lah.
Oh, just based on voltage and current.
Betul. So basically kita buat offline punya method lah.
Yes. Also, that one can be more difficult to make it into this form, right?
Correct.
To identify it into this form, unless is it easy to diagnose it based on this characteristic?
Characteristic no issue, kita boleh detect. Cuma dari segi interpretation tu dia ada banyak lagi orang kata percanggahan lah.
Because I think the diagnose or the identification, what I understand is like from the detector, the PD detector itself.
Betul. Agree. Dari segi pattern recognition ni pun is basically the same je lah sebenarnya.
Cuma if you were to come up with that, you have to do many tests, is it, to be able to be firm that one means that particular reason.
Yes, betul lah. Cuma tu je lah sebab coupling capacitor ni kita tak tahu macam mana, what is the best and what is the different ni kan.
Yes.
Tapi achieve je PD tu kan, as long as once voltage tu ada, PD tu ada, then benda tu dia dapat je.
Yeah.
Dia measure je lah.
The different ni apa benda, accuracy.
Yeah. I'm not sure as well, like but it may be possible lah to give different because we know the purpose, and then maybe one could be more accurate than the other, also not in that area.
Understand. Okay, thank you Dr.
Okay,
thank you Syukri. Ada lagi soalan? Siapa resign ke tadi? Bunyi tang. Okay, so kalau tak ada, dan saya pun dah kesan kat Prof Normiza dah lama, dah lebih masa, dah dekat pukul 12 dah. Kita janji 11.30 je kan. Okay, so terima kasih. Thank you very much to Prof Normiza for sharing session with us. And for students, there will be one more sharing session untuk siri 2. Nanti kita akan buat bulan 1, bulan Januari. So nanti kita akan buat announcement. So thanks again Prof Normiza. I hope to
Thank you all.
at Unimed pula. Okay, terima kasih semua. Have a great weekend everyone. Thank you very much. Assalamualaikum.
Waalaikumsalam. Thank you all for and thank you Dr. Hazia for the invitation.
Thank you.
All right, bye.
Bye.
Okay, bye. Assalamualaikum.
Prof.
Okay, bye.
Thank you, Doctor.
Thank you. Don't
Thank you,
forget to
Doctor.
cari attendance. Attendance jangan lupa.
All right, thank you. Bye.
Thank you Normiza. Bye.
Ya, Ustazah.
Okay, thank you.